Hi, it's Mr. Benson here with the last of the 2011 motion questions. This feels like it's going on forever, but we'll get there pretty soon. Okay, so the next 4 questions. So it's one of these spring questions, so we've got to think about strain potential energy. We've got to think about energy transformations. We've got to think about strain and the spring constant. So that should give us some idea about the kinds of equations we're looking at. Without the mass attached, which means the weight force is 0, it has an unstretched length of 40 centimeters, a mass of 1 kilo is attached, then the spring has a length of 70 centimeters. So, given a bunch of information there, mass, which is going to become a weight force, and we're given some extension measurements there. Now we've gone from unstretched of 40 to 70, which means we have got a displacement on the string of 30 centimeters or 0.3 meters. We know that W equals force equals W, which equals mg, so it is 10 times 1, which equals 10 newtons. So F equals kx, I'm just going to ignore the minus sign for this at this point. So 10 newtons is k times 0.3, k equals 10 over 0.3, which is 33 newtons per meter. Not newton seconds or anything weird like that. Okay, so we've answered our first question there. Moving on. The spring is now pulled down a further 10 centimeters to 80 centimeters and released so that it oscillates. The gravitational potential is measured from the lowest point, the 80 centimeter point, and we're given some graphs here. Now, we've looked at questions like this before, and it's good to remember a few things about the motion. So when it's oscillating, well, at the top of its motion here, well, what do we know about it? Let's have a think about this one here. Now, this is an interesting situation, actually. It is slightly different to the exam question we've looked at, because the point at which strain potential energy is 0 is actually up here. So down here, the strain potential energy is not 0, but it is at a minimum. At this point here, gravitational potential energy is at a maximum. Down here, gravitational potential energy is at a minimum, and E strain is at a maximum, and it also equals the total energy at that point. There are a few other things we know about. Kinetic energy is 0 at these 2 points, and it's a maximum in the middle. And as I've shown you before, you can get a quite elegant solution to these problems when you do some simultaneous equations, because we know some things about the motion, and we know some things about the equations that we can use to describe the energy at different points, and so perhaps simultaneous equations will be useful, or perhaps not. We'll have a look at the questions. So, we've got some information about graphs, and we need to match them up with what's going on. So our first question, which of the graphs best shows the variation in the kinetic energy of the system plotted against the length of the stretched string? Now, I've already discussed some stuff which helps us understand what's going on there. Now we know that kinetic energy is 0 when the weight is at the bottom or the top of its motion, and it's at a maximum in the middle of the motion. Now the only one that comes close to it is D, where you've got the minima at 70 and 80, and you've got your maximum in the middle there. So D must be our answer for this first question here. Which of the graphs best shows the variation in the total energy of the system of the spring and mass plotted against the length of the stretched spring? Now, this is a trick question. Well, it's not a trick question, but the trick, if you like, is that there is no variation because energy is being conserved. So we're looking for a graph where there is no variation, and that is C, where the energy is constant no matter where we are. So our answer to that one is C. Question 19. Which of the graphs best shows the variation in the gravitational potential energy of the system of the spring and the mass? Plotted against the length of the stretched spring. Now, I've discussed this a little bit earlier. We know that the gravitational potential energy is at a maximum at 60 centimeters and a minimum at, in fact, it's 0 effectively at 80 centimeters. The other thing about gravitational potential energy is it's linear, so it's a linear relationship against the displacement. So what we're looking for is something that is 0 at 80, has a maximum at 60, and has a linear form. Now the only one that looks like that is B. Moving on, which of the graphs A to H best shows the variation in the strain potential energy? Plotted against the length of the stretched spring. Give you reasons. Now, when we have a look at this, there's a couple of things that we need to think about with strain potential energy. Now, when we think about that one, E strain is a half kx squared. Now, this is really important. It's not a linear function, so it's going to look like a parabola. What else do we know about it? It's going to be lower at the top, so the strain is going to be at its maximum value at 80 centimeters. It's going to be at a lower value at 60 centimeters, but it's not going to be 0 because that would only happen at 40 centimeters, and it doesn't oscillate up to that point. So it's going to look like a piece of a parabola that's got a maximum at 80. Now, the one that best looks like that is F. G is also a piece of a parabola, more or less, but it's the wrong way up. So that's not helpful. If you think about F, if we were to continue it along to 0 like that, that was terrible, that's a bit better. So we'd have the shape there. As we continued on further, our strain potential energy would be rising up like that. So that's clearly the shape that we're looking for. So our answer for this one is F. Now, giving reasons, this is actually a little bit tricky to explain nicely, but along the lines of what I've said before. So it's going to have a max at 80 centimeters, minimum at 60 centimeters. It's parabolic with the intercept at I believe 40 centimeters. So that's not a bad explanation for that one. Okay, moving on. Somewhere in space there is a small spherical planet with a radius of 30 kilometers. Now that is very small. First thing we need to think about with this bit of information is it's not in meters, so we've got 30,000 meters. A person living on this planet visits Earth. He finds that he weighs the same on Earth as he did on his home planet. Now that's important because on Earth G is 10 newtons per kilogram, which they just tell us below anyway, but that's important because they're saying that the gravitational field strength is the same on both planets. This is the stuff about the Earth. Universal gravitational constant. What is the now the first question, what is the value of the gravitational field on the surface of the visitor's planet? They've just told you the answer, it's 10. Now they give you all sorts of information here, but you don't need to do anything with it. So you don't need to do any calculations at all. They're telling you what the value is. Okay, I didn't need to leave that empty space. What is the mass of the visitor's planet? Now this is where we've got to do a little bit of calculation. So explain your answer by showing clear working. Now we don't need to know the mass of the visitor here because we can just use this formula. So G equals m1 over r squared. So we know G is 10. We know big G is the universal gravitational constant. M we are trying to find, question mark. R is the radius of the planet, which is 30,000 meters. So all we've got to do is substitute in. So you could substitute and rearrange, or you could rearrange and substitute. Now I'll just rearrange this first. M is going to be GR squared over big G. Gotta get my calculator out here. 10 times 30,000 squared divided by 6.67 times 10 to the negative 11 gives us a mass of 1.35 times 10 to the 20 kilograms. Now, just, as a comparison here, although this has got nothing to do with the question really, the mass of the Earth is 10,000 times greater than that, 4 orders of magnitude. So this is how you can have something that is considerably smaller in radius than the Earth, but could have the same sort of gravitational field. Okay, the visitor's home planet is around the star at an orbit of 1 times 10 to the 9 meters. So this is R. And we've got the mass of the star here. Now, what is the period of the orbit of the visitor's planet showing or working? Now, there's a couple of ways you could do this one. You could do it in multiple steps, where you think about the gravitational force, which is the same as the centripetal force. Therefore, you've got the centripetal acceleration, and therefore you can work out the velocity, and then you can work out the period. That's just taken us 4 steps. So rather than that, we can look for a different equation to use. Okay, this is where we want to use the equation that you will not find on your cheat sheet. So this is where we've got the radius cubed over the period squared is gm over 4 pi squared. So this one, like I've said, not in the formula sheet, should be on your cheat sheet because it allows you to do a lot of stuff in one calculation. I've also mentioned before you can derive this. It takes ages and it's easy to get it wrong. So you don't want to be doing that. So we're looking for the period of the orbit of the visitor's planet showing working. So we could substitute stuff into this and then rearrange, or alternately we could rearrange it first. So we want to find the period. So I'm going to inverse both sides of my equation. So I'm going to get the period squared is going to equal 4 pi squared r cubed over gm. And then I'm going to substitute in all my stuff and square root all of this. So this period is going to be the square root of 4 pi squared r cubed over gm. So with things like this, all you've got to do is be careful when you're substituting on your calculator. So 4 times pi squared times so 1 times 10 to the 9 cubed divided by g, which is 6.67 times 10 to the negative 11 times the mass of the planet, which is 5.7, sorry, the mass of the star, times 10 to the 25. Now that's a ridiculously small mass for a star. In fact, it wouldn't be a star, but that's okay. Again, questions can be silly as long as you work them through carefully. So what I've got is I've got 3, now I'm going to put this in engineering notation, 3.2 times 10 to the 6 seconds. Now that's a perfectly reasonable answer if you wanted to convert it into something else. So if we divided that by 3,600 to get hours, you get 895 hours. and that is 37.3 days. But in terms of standard units, this is the answer that we want. Okay, so although that's a fairly tricky equation to use, it's the best solution for this kind of question, so make sure that you're familiar with it and you can use it. Okay, this is the end, finally, because that was fairly epic and I'm sorry it took so long. I want you to go through your own work, try and figure out where you made mistakes, discuss it with each other, and if that doesn't get you to understanding what went wrong, ask me about it, and I will spend some time with you on these particular questions.